And let's try to do some statistics now related to the regression setting that we were talking about. We quantified how the weight was related to height. We quantified it based on a sample of 11. That comes with probably pretty high statistical uncertainty. And you might raise the research question, if these were more unknown things we were looking into, the research question could be, is there at all a relationship between X and Y? Can we prove that with our experiment, that there is a relationship between the X and the Y? I mean, in this case, we have a pretty good feeling that that will be the case. But could we prove it? That's the thing we should think about. That is called inference, I hope you remember. We have to do some statistics. We split it in two small subsections. We split it between doing statistics for the intercept and the slope, and then secondly, we do statistics for the line as a sort of joint thing. Because now we have more than one thing in play, so we have to be a bit thinking us a little bit about in how we do it. Yes. Here's the formula of the model. The first thing we should use and think about is the fact that the line, as a way of telling the story of what is going on, does not tell the full story. We do, in our model, in our way of looking at it, we do have some errors that actually we usually assume, this is the classical statistical regression model, that we assume that the errors behave like a normal distribution. We assume that the way people do not fit the line, the way they deviate from the line, follows a normal distribution. So the biological variability is a normal one. It may not be true, but that's the assumption at the outset. And then we have, as a first step to be intelligent, we need to quantify the degree to which the points do not lie exactly on the line. How much different from the line are the points? Well, this is a variance now, but it's not the variance that we are used to seeing. Please note that I gave it a subscript E. The variance here is taking the sum of all observations, each individual observation, subtracting the line. Like this. Subtracting the line points from each. This is exactly the least square number. This is exactly the number we have made small as possible by the way we chose the line, right? We take this is a value that expresses how much do all the points added up altogether deviate from the line. If all the points are exactly on the line, this number will be 1. If all the points are far away from the line, this number will be large. And then we average. Like when we compute a variance, we always average. Here we have to be careful, because now we don't average with n, and we don't neither average with n or n minus 1. We average by n minus 2. From the same arguments, which I didn't give you in very much detail, that we use n minus 1 for the variance, we are going to use n minus 2 for this variance. I should say the usual variance, we use n minus 1. This is another variance. This is kind of a line variance, you could say. How this is a deviation from the line, because actually we use 2 points to compute the mean, the intercept, and the slope. Another way of saying it, if I only have 2 data points, I could put in a line exactly in the 2 data points. And this number will be 0, right? Because if I have only 2 lines, they will be exactly on the line. But that is to say that I know nothing about the variability. And that is, again, saying it makes good sense to divide by n minus 2, because then what do? I divide 0 by 0. If I'm a mathematician or anyone else, I have to realize if I divide 0 by 0, I have to give a question mark as the answer. I don't know what the answer is when I divide 0 by 0. So that is correct answer. If I have only 2 points, I don't know what the underlying deviation is, because I've just fitted exactly something. there is a formula for this one here. This is the defining formula. This is a hand calculation formula, if you want. And I'm not going to prove that these two things match up. So this is for hand calculation. Having computed this variance estimate, so there is an underlying variability in the system, sigma, and we have computed sigma hat here, the estimate of the variance. This is the important tool to do statistics. Variability is the important tool for doing statistics. Now we can do statistics for the intercept, and we can do statistics for the slope. Let me begin. I should change the order of these two slides, because usually I would begin with doing statistics for the intercept, and then maybe I'll never ever do the statistics. Wrong word here. Usually I would start by doing statistics for the slope. That is the most important thing. And then for most cases, the statistics for the intercept I wouldn't even do. I wouldn't care. But I mean, I share it with you. You can do it, and R will give it to you. So all programs will give it to you. The point is, we can do hypothesis testing and we can do confidence intervals. And today we're going to do it a bit more rapidly. I'm not going to spend 15 minutes on one confidence interval and 15 minutes on another hypothesis test, because we can do both things for the intercept, both things for the slope, and then in fact we can do some things for the line also. So we're going to do many things. So I'm going to be more rapid now since we're at the end of the course. I maybe would like to test hypotheses about the slope. One hypothesis often tested is this one. Which would be the one that we should use if we should test, is there a relationship between x and y? Understood linear relationship. Is there a relationship? Something went black here, Georgi, but I guess my computer is okay?
It's okay here.
Is it the live streaming that is gone, or? Yeah. Technical error. I was just checking how fast you could do. You did it in 3.5 seconds. We may get some stats on that. Okay, thanks, Georgi. Sorry about that. Should we try again? No. Sorry about that. Is there a relation between the two things? There is a test statistic here that takes the computed slope, subtracting the theoretical slope, and that follows a t distribution. So we should use a t distribution. Actually, there's a bit of confusion here. I think it's more easily understood if we say beta minus b naught. Here it is. There is sometimes a notation challenge here, depending on whether we consider those statistics as their random versions or as their actually computed versions. And there are actually a bit of a lack of precision in because in the way we deal with this usually, and also here. But here is the way I like it more, that we use b naught as the hypothesized value, and we use b for the computed values. So when we compute the statistic, here it comes. We compute it by taking the observed b, subtracting the hypothesized b, and then dividing by the SE times square root SXX. This is the most meaningful way of putting it, as the computed version of the test statistic. The random version of the test statistic then follows, statistical theory tells us, a t distribution. So we can use usual t things in doing statistics. Then I jump back, and I should do the similar correction here, like this. This would be the test statistic to compute for the intercept. what I'm saying is, let's get back to why I'll do that later when we look at some results, why I said maybe we rarely would be interested in actually doing this for the intercept. I'll get back to that when we look at the result. We can do it if we want to do it for the intercept. So there is a formula for how to do t-test statistics for the intercept and for the slope, and the same building stones also gives confidence intervals for, and here I don't have to correct anything, they are given in a meaningful computational way. We can do confidence intervals because statistical theory tells us the sampling distribution of the slope and of the intercept. So we use the same thinking. We should think, what if I once again take a sample of 11 of you and compute the intercept and the slope? Let's focus on the slope now, for instance. Then I get another slope value. I don't get 0.55, I would get something differently, right? So, and what if I do it a third time and a fourth time? Well, statistical theory can find out what is the variability of such a computation. Now it's a more complicated computation than just computing a mean. It's a slope we compute, but this theory can still tell us how will this vary from sample to sampling. There is a well-known sampling distribution, and for instance, this number here, you could also call this is the sampling distribution standard deviation of B, considered as a random variable, considered as something that varies from sample to sample, right? With the lack of notational precision here, that we don't usually use a capital B, which I should do, but I won't do it now because it's not part of the book notation to make this distinction. And we can definitely live with that. I think maybe it confuses more if we do. A B will change from time to time, and the theory tells me how much can it change. I can do a confidence interval, and I can do hypothesis testing, right? It's not more complicated than that. We need those building stones, the computations from the means and the variances and the covariances to be able to compute the things, or we can use R, which I'll show you in a sec again. That was statistical inference for slope and intercept. Confidence intervals and hypothesis testing. The formulas are there, R can give it to us.